Good morning, everyone. Today we shall conclude our discussion on available expressions analysis problem, and we compare and contrast it against the live variable analysis problem which we have studied in the previous lecture. And in the next class, we will take a look at, we'll spend a couple of lectures on taking a look at the internals of the LLVM compiler. Just to recap the available expressions problem. So we say that an expression is available at a program point P if all the paths starting from the entry program point to P contains an evaluation of that or a computation of that expression. And after the computation of the expression, the operands of the expression are not modified. Like for example, if you take this example, in this example, let's say these are the three different paths from start to the program point P. And along each of the paths, the expression A star B is computed. And after the computation of A star B, the operands A and B are not modified. So because of that, we say that the expression A star B is available at the program point P. If you see the example, the middle example here, the expression A star B is available along this path, but in the middle path, it is not available because after the computation of A star B, one of the operands A got modified. So because of that, it is not available along this path. Since it is not available along this path, we say that at the program point P, the expression A star B is not available. So we don't consider it as a redundant computation. And if you take the third example here, in the third example, the expression A star B is available on the first path, it is available on the third path, but along the middle path, second path, the expression A star B is not computed at all. So again, so because of that reason, we say that the expression A star B is not available at the program point B. So this is the basic definition for when we say that an expression is available at a program point P or not. And the problem that we are looking at is at given a program point P, we want to compute the set of all expressions that are available at the program point. So in fact, we can consider a universe of expressions. This is the universe U of expressions. In this universe U of expressions, so we have different expressions, E1, E2, E3, and all these expressions, they are, we consider all the textual expressions which are occurring on the right-hand side of some statement, some tuple in the control flow graph. Because otherwise, like if you just take arbitrary, all possible expressions, x plus y, if there are n variables, so there are n possibilities for this operand, and say similarly there are n possibilities for this operand, and if there are k different operators, then there are k, so these are k different possibilities for the operator. So overall we have kn square different uh, expressions possible in the program. And so unnecessarily, even if the number of variables are 10, then what happens is the number of expressions to consider will be large, and most of them, 99% of them, could be useless. So what we do is we can just scan the program and look at those expressions which are occurring on the right hand side of some statement. Like if we have something like z is equal to x plus y, then we consider expression this expression as a valid expression belonging to this universe, and we can give a name to it by say, let's call it as expression E1. All right. So now our goal now is to compute the set of expressions that are available at a program point. That's our goal. So similar to live variable analysis problem, we will try to build up the intuition from ground up. So let's say we have a program point P here, and so we have a statement x is equal to y plus z. Let's call this expression y plus z as e. So let's call it as e. So p prime, this is the program point p prime after the tuple x is equal to y plus z. And we say that if you see the set of expressions that are available at the program point p prime, AE stands for available expressions. Available expressions at the program point p prime is equal to, you can see that the expression E is available at the program point P prime. It is computed here. It is downwardly exposed. So, so because of that, the expression E is available at the program point P prime. So what it means is, like, for example, if you have something like W is equal to Y plus Z, since Y plus Z is available, the expression Y plus Z is available at the program point P prime, we can remove this computation Y plus Z here and use X. We can replace the statement with W is equal to X, for example. So, well, anyways, so the set of expressions that are available at the program point P prime is equal to set of expressions that are available at P. Look at all the expressions that are available at P. So we will visit this, that is a, yeah, so let's put it here. And then, so we will see what this term is. But definitely at program point P prime, the expression E is available. So we take the union of it, and from all the expressions that are available at program point P, we will remove what is called as a kill X set. So what is kill X set? Kill X is equal to set of all expressions such that E contains X as an operand, variable X as an operand. Like, for example, if we have an expression such as, so y plus x, okay, the expression y plus x, let's say you have at the program, before program point P prime, you have something like program point P double prime, and here you have something like u is equal to x plus k, something like this. So this expression x plus k is available at the program point P, but it is not available at the program point P prime because x is getting modified by this tuple. The operand x is getting modified by this tuple. So because of that, we want to kill it. In general, look at all the expressions that are available at the program point P, and so consider those expressions which has x as an operand. And we want to remove them from the available. As we propagate this available expression set here, we filter out those expressions which contain x as an operand. And we include the new expression y plus z here, and we include the new expression y plus z as the available expression at the program point P prime. So that's what we are trying to do. So there is a, so now let's say, so this is, so let's consider another case. In this case, let's say x is equal to x plus z, and this is P prime. So if we consider this case, then what happens is, so according to the definition, so if you can, from this, from the definition of available expressions, you can see that the expression x plus z is not available here because it is computed here, but its operand is getting immediately modified. So because of that, it is not available at the program point P prime. Okay. So, but then, so according to this relationship between the available expressions at program point P prime and P, E gets included. So this, there is a problem in this relation when we encounter tuples such as this. So how do we solve this problem? The way we solve this problem is we say AE prime is equal to, in the available expression set P, you first include E. From this, we eliminate the kill set. So when we have this, what happens is you first include X plus Z in the, and then, so like in this particular example, so what happens is E belongs, so you can see E is present here, but E is present here also, because X plus Z uh, belongs to the kill set kill of X. So E is present here, so E is present here, so it gets knocked off. So when we look at the program point P prime, the expression E is not included. So by rewriting this relationship in this particular fashion, we are able to take care of this particular case too. This particular relation takes care of this case and this case too without any problem. So the point is, when you are trying to set up relationship between these data flow relationships, so you have to be careful in understanding different cases. And so if you don't pay attention to them, we may end up having bugs in our data flow analysis formulation, and it would impact the semantics of the program that is being compiled and optimized. One important observation I would like you to make is in the live variable analysis problem, we are propagating the information in the upward direction. So just to recall, this is what we have seen in the last class. So if we have something like P is P, X is equal to Y plus Z, P prime. So what did we say? We say the set of variables that are live, you look at variables that are live at the program point P prime, and so we push this information, this set upwards. And when we push this set upwards at program point P, we say that the variables Y and Z, they are live because we are using them in this tuple, and then yeah. And then so the variable X, we take it out from the liveness set, because X is being defined here. Like for example, at this point, if you have X, it could be live here, but X is not live here at the program point P prime, because it is being defined on the LHS. So live of P prime, so live of P, this is what we did in the last class. Live of P is equal to live of P prime union Y comma Z minus X. So here in the live variable analysis problem, we are pushing this set upwards, but whereas in the available expressions analysis problem, we are doing this computation in a forward direction. So this is forward direction. This is forward direction. And this is backward direction. Now let's look at what happens if pointers are being used in our program. So the way we handle pointers in this particular case is when we are dealing with available expressions is relatively simple. So let's say you have some statement like star P is equal to T, P prime. So the case where the other case where we have something like P, T is equal to star P, we ignore this case. We don't worry about it. It's okay. So you're doing reading something from the memory, so we don't deal with it. We just leave it as it is. So we don't we ignore this case. We don't need to worry about it. But if you look at this case, this particular case is a tricky case because let's say if an expression x plus y is available here, let's say an expression x plus y is available here, and when we are trying to push this expression x plus y through this tuple, then whether the expression x plus y survives this, gets filtered out or not, depends on whether the pointer p, let's use ptr instead of p. So, ptr is equal to t. So it depends on whether this expression e gets filtered out or not, depends upon whether the pointer variable points to variable x or y. If the pointer variable points to x or y, then the expression e gets filtered out. But if it doesn't point to x or y, then the expression x plus y survives. And in order to figure out all the variables to which PTR points to, we have to perform a pointer analysis on the control flow graph. And if you don't have a pointer analysis algorithm, then we have to conservatively assume that PTR could be pointing to any of the variables that are there in the program. And because of that, so what happens is when we are trying to push an expression across a statement like this, all expressions get killed, because in the absence of a reasonable pointer analysis algorithm, we just have to assume that PTR could be pointing to any of the operands, and so we end up killing all the expressions. That means we will end up losing out on many optimization opportunities. So it is important to have a good pointer analysis algorithm in our compiler so that we can use it information to facilitate other optimizations. Great. So if you want to formally set up the data flow equations, so here the set of expressions that are available at program point p prime is equal to set of expressions that are available at p minus set of expressions e uh, such that x such that the variable x belongs to points to ptr comma p. This p is a because at program point p, what are all the potential variables to which the pointer variable is pointing to? X, or similarly, or y belongs to points to ptr. Just want to make it clear here that so this is a pointer variable that we are talking about, and this is the program point. So now what we have is, so if we have a basic block, so if we have a basic block, this is our basic block. Maybe I should draw it a bit down. So if we have a basic block, and if we know the set of expressions that are available at the beginning of the basic block, so at the beginning of the basic block, if you know the set of expressions that are available, then we can propagate this information, push this information through each of the tuples in this basic block, and we can compute at different program points in the basic block what are the expressions that are available. So this is all great when we are working with straight line sequence of code, but if the code is not a straight line, but we have to handle control flow in our programs. So how do we handle control flow? So let's see. Yeah. So, and then again, let's say the set of, let's call this as the basic block B2, and this is as basic block B3, and this is as basic block B4. And so based on this observation, let's say this in of B2 is a set of expressions that are available at the beginning of the basic block B2. Then a set of expressions that are available at the end of the basic block B2, it is a function of the set of expressions that are available at the beginning of the basic block. And let's consider this control flow here. In this control flow, if you see the set of expressions that are available at the beginning of the basic block B4, it is equal to, that is in of B4, it is equal to out of B2 intersection out of B3. So we say that a way expression is available at this program point at the beginning of this basic block if it is available along this edge and if it is available along this edge. So because of that, the confluence operator, so remember this is the confluence or meet operator. The confluence or meet operator, it is intersection. Whereas in the case of live variable analysis problem, the confluence operator is a union operator and the structure is also different. So there, so if we have a basic block such as this B1, so we say that a variable is live at the end of this basic block if it is live at the beginning of this basic block or if it is live at the beginning of this basic block. So the way we set up the confluence operation here is out of B1 is equal to in of B2 union in of B3. So here the computation of the outset for the basic block B1 depends on the insets of its successors, and the way we merge that information is a union operation. But whereas if you see here, the expressions that are available at the beginning of this basic block, they depend on the outsets of the predecessor basic blocks. And the way we merge that information is by using an intersection operation. And from this, you can see the information again, this information that we are computing here, it is going in the backward direction. So the whatever this in B is getting propagated here and in of B3 is getting propagated here, and then you compute out of B1 and then we propagate this information now. But whereas if you see here, so we compute, so we have in of B2 information, in of B3 information, we propagate this information forward, we propagate this information forward, and then we merge this information to compute the in of B4, and then we propagate this information forward. So this is what is called as a forward data flow analysis problem. So the problem that we are looking here, this available expressions analysis, this is a forward data flow analysis problem. Data flow. And this is a backward data flow analysis problem, live variables. Backward, I just use DFA as a shorthand for data flow analysis. So that's one comparison. The second comparison here is the meet operator. Okay, so the meet operator, this is an intersection meet operator, but whereas here, this is a union meet operator. And this intersection and union, it doesn't depend on whether they are forward data flow analysis or backward data flow analysis. You can have a forward data flow analysis problem with a confluence operator, which is union, and you can have a backward data flow analysis problem with a confluence operator, which is intersection. So don't get confused on this front. Forward data flow analysis merely says that we are pushing data in the forward direction, and the backward data flow analysis merely says that we are pushing data in the backward direction. And the confluence operator, it depends on whether, depends on the nature of the data flow analysis problem at hand. So if we keep going further here, so let's say if we finish the control flow graph, it may look something like this. So this is basic block B1, and then you can have the entry basic block. And then we can have the boundary condition that in of entry is equal to empty set. No expression is available at the beginning of the basic. Again, in practice, so if your function has expressions involving variables that are global in nature, then possibly we can use interprocedural analysis to initialize this in of entry set to a better set, which is right now we are, this is a safe initialization, but we might be losing out on some optimization opportunities. But if we do interprocedural analysis, we might be able to figure out that some expressions are available here and they can be included here. And those expressions involve operands from global variables, for example. And then we can have an exit. There's some problem. Not able to write here. Yeah, great. So in order to complete the story, so again, if you see here, out of B4 is equal to, you can see out of B4 is equal to f of in of B4, and out of in of exit, let me write here, in of exit is equal to out of B4. Similarly, here we can write, like for example, here in of B3 is equal to out of B1. Similarly, here in of B2 is equal to out of B1, and yeah, so same. So here out of B1 is equal to f of in of B1, and if you look at in of B1, it is equal to in of entry, out of entry. Out of entry and in of entry, they are the same. So like this, associated for the whole control flow graph, we can set up these relationships and we can try to solve for these sets. And as you can easily note, that in this, if the graph control flow graph doesn't contain any loops, you can sort this control flow graph in a topologically sorted order and compute various sets by propagating information in the forward direction. Like for example, if you see that this information, we know in of entry is equal to out of entry. So from out of entry, we can compute in of B1. From in of B1, we can compute out of B1. And if we know out of B1, then this information propagates here, and this information propagates here. And then, so we can, from in of B2, we can compute out of B2, and from out of, so and from in of B3, we can, so from in of B3, we can compute out of B3. So I didn't write here. Let's say we can have something like out of B3 is equal to f of in of B3. And once we have this, we can, so you can use this information here, and you can use this information here. And so that's how you can propagate this information forwards, and finally we can compute. But then, as we have seen in the last class, this becomes an issue if there is a cycle in the control flow graph, which is usually the case. So let's say that there is a cycle in the control flow graph. So let's say we have a cycle like this. So if we have a cycle like this, then what happens is then we can say that in of B2, if you look at this in of B2 function, let's see this in of B2. In of B2 is equal to out of B1 union out of B2. So in of B2 depends on out of B1 and out of B2, and out of B2 depends on in of B2. So there is a circular dependency. So you can see, so in order to compute in of B2, we need out of B2. And in order to compute out of B2, we need in of B2, and there is a circular dependency. And when there is a circular dependency, so we need to come up with algorithmic approaches to handle these circular dependencies. So one particular approach which we have seen in the last class and in some classes before also is iterative fixed point algorithms. So now let's see iterative fixed point algorithms for the available expressions problem, how it looks like. So here we have, let's take a look at this example. So this is the example I would like to see, but we'll get there in a while. But then, so the formulation of available expressions that we have seen just now is at a per tuple level. That is how available expressions between two consecutive program points are related to each other. But if you look at the basic block level, you can note I'm not able to write. Just give me a minute. So there is some problem in. Yeah, I think there is a problem. Let me. Can you see the screen now? Great. So if you see for a basic block B, so in B is a set of expressions that are available at the beginning of the basic block, and out B is a set of expressions that are available at the end of the basic block. And Gen B is the set of expressions that are evaluated or computed in the basic block, and after the last evaluation of that expression, the operands of the expression are not modified. Like for example, if this is a basic block, in this basic block, so you see something like x plus y on the RHS, and after the computation of x plus y, so the variables x and y, they are not modified in this portion of the basic block. In which case we say that the expression x plus y is downwardly exposed. It is downwardly exposed. And it belongs to the gen set. And the kill set consists of all those expressions whose operands are modified. Like for example, if we have something like z is equal to some tuple, then any expression which involves the expression z, it gets killed. So an important thing to note is the gen B and kill B sets, we can compute them just by looking at the basic block without referring to the rest of the control flow graph. But if you want to compute out B and in B sets, maybe you need to refer to the rest of the control flow graph. But Gen B and Kill B sets, they are constants and they don't change, and they depend on, they are completely a function of the current basic block under consideration. There is one more case also, like for example, this takes care of the case which we considered before. Let's say if you have a statement such as x is equal to something. So if you see this thing, and let's say that this expression x plus y, we call it as E. So the expression, so E is present here because it is downwardly exposed, and the expression E is present here. Let's say the expression x plus y is available at the beginning of this basic block. It is available at the beginning of this basic block. So what happens is the expression E, it is available at the beginning of the basic block. It gets killed because its operand is getting modified, but then it is getting locally regenerated through this Gen B set. So we are in a good shape, so there is no problem. So please keep that in mind. So with this, and then the next idea is, the in B sets, we have seen already the set of expressions that are available at, if you have something like this is the basic block B, it has multiple predecessors. So the set of expressions that are available at the beginning of the basic block B, you take the expressions that are available at the end of the predecessor basic blocks, and you take the intersection of them, and you get the in B set. So these are the two data flow equations that are associated with the basic block B, with every basic block B. And for every basic block B, if you set up these relations, you should note, you should know, as I emphasized earlier, these Gen B and Kill B sets are, they are completely a function of the basic block itself. They don't rely on anything else outside the basic block. So we set up a system of equations or constraints by writing down these two these equations for every basic block, and then we solve for it. So this is what is called as a transfer equation. This is what is called as a transfer equation. And this is the meet operator or meet equation, whatever you want to call it. And what is the algorithm for this? So you know that the boundary condition that the expressions that are available in the entry basic block is the null set, unless you do some interprocedural analysis and be able to get a better estimate for this set. This is what we start with. And so here, so we have to come up with an initial estimate of the available expressions for different basic blocks. So here we start with an overestimate. U is the universe of all expressions. So here, important observation, overestimate. And then what we do is, for every, this is the micro iteration, this is the micro iteration, and this is the macro iteration. Within a macro iteration, we visit all the basic blocks. And visiting each basic block, it's like a micro iteration. The number of times we go through this block, this inner for loop, it is when we instantiate it once, or when we call it once, is equal to the number of basic blocks present in the control flow graph. But the number of times we go through the outer while loop, it depends on the control flow graph at hand. So now this is, so what is the idea here? You start with an overestimate and we keep improving that estimate. That is the idea. Let's look at an example. So here is the example control flow graph that we have. And this is how the algorithm proceeds. So as you can see, we started with an over approximation. The initial approximation is a over approximation. And in iteration 1.1, so what we are doing is we are saying out of B1 is equal to, yeah, so what do we do? Just take a moment. That's true. So out of B1 is equal to in of B2. Did I get something wrong? What is expression? Yeah, I think we are good. So yeah, if you see, this is the initial approximation. So remember, out of B1, it depends on out of B1. It's a function of in of B1 and the gen B and kill B sets. So if you see the expressions that are locally generated in the basic block B1 are the expressions A plus B and A star B. So because of that, they are included here. E1 and E2 are locally generated in the basic block B1. And so out of entry, it's so the way we kind of yeah, let's and we consider this. Okay, let's stick to this, and then when we consider basic block B2, when we consider basic block B2, in of B2 is equal to out of B1. In of B2 is equal to out of B1. So what happens is this information, it gets propagated here. This information gets propagated here. And this, we want to pass this information through this basic block B2. But when we pass this information to the basic block B2, no expression gets locally generated, no expression gets locally killed. So this will just go like this. And now when we come to basic block B3, out of B3 is equal to in of B2. So this information gets propagated here. So here what we have is expression E1, E2 is here. But when we try to push this information downwards, what happens is the expression A plus 1, yeah, it gets locally generated but gets killed, but A plus B gets killed. A plus B is expression E1, so it gets killed because one of the operands is getting modified. But then it gets regenerated also. Yeah, that's the point here. So E1 gets killed but locally generated. But if you look at E2, E2 is A star B. It gets killed but it's not locally regenerated. So what happens is as we push this set E1, E2 by applying the transfer equation, this is what we get. So and then we iterate like this. So just want to make this clear, just this last example, I'll just make this clear because I think I may have. So this is E1, E2. So this is, so A plus B gets, if you see the gen set of basic block B3, gen of B3, it consists of only expression E1. And if you look at kill of B3, it consists of expressions it consists, yeah. So it actually kills all the expressions, E1, E2, E3. So, but what happens is, so when we push this set, this inset through this basic block, these E1, E2 expressions gets killed because, but then the expression E1 gets locally generated. And that's what happens. This is E1. And so what happens finally is at the end of iteration, macro iteration 1, the current estimate of various sets, in and out sets, is given by what you have on this slide. With this current estimation, we iterate again and we improve our estimates, and then we iterate again. So at the end of iteration 3, we have the correct values for different in and out sets, but we need one more iteration in order to figure out that we have converged. So that is how fixed point algorithms work. And again, the idea of convergence, these sets are monotonically increasing. So there are only finite number of expressions in the program. So the size of these sets are finite. So they cannot keep on increasing. So this algorithm has to terminate. And the final solution that we get, it depends upon the initial estimate. Whether we are doing an overestimate, whether we are doing an underestimate, or if you start with a different estimate point. So the final solution, it in fact depends on the initial estimate that we, initial approximation we start with. But the rule of thumb is, in this particular available expressions problem, the meet operation is intersection. When the meet operation or confluence operation is intersection, you overestimate. In the case of live variable analysis problem, the meet operation is union, and in that case, we underestimate. So this is the idea. See, let's keep going. So now what I would like you to do is consider this example control flow graph. In this control flow graph, if you see at the basic block B2, at the beginning of the basic block B2, the expression A plus B is available. Because if you take from the entry path, any path starting from entry to this point, the expression A plus B is evaluated, but it is not killed. So what happens is the expression A plus B, if you look at this program point P, the expression A plus B is available. But if you start with an underestimate, then what happens is we will end up computing saying that the expression A plus B is not available at the beginning of the basic block. In this particular example, it's not really a big deal because we are not losing out on any optimization opportunity. And the homework problem for you is come up with a control flow graph inspired by this example, where an underestimate leads to an incorrect estimate of available. We end up computing available expressions analysis in such a way we lose out on optimization opportunities. But in this particular case, theoretically speaking, at this program point P, A plus B is available, but we say it is not available if we start with an underestimate. But it is not a big deal in this example because we are not losing out on optimization opportunities. So I want you to come up with an interesting example where underestimation leads to a lost optimization opportunity or some incorrect program transformation possible. To summarize, this is what we have. Let me This is the summary of data flow analysis. So we have seen two data flow analysis problems. One is live variable analysis problem, and other is available expressions analysis problem. In live variable analysis problem, at every program point, we want to compute the set of variables that are live. In the available expressions analysis problem, at every program point, we are trying to compute what is the set of expressions that are available. Live variable analysis, it's a backward data flow analysis problem. We try to push information upwards. In available expressions analysis problem, it's a forward data flow analysis problem where we push the information in the forward direction. And this is how the transfer function looks like in both the cases. Incidentally, they are looking the same. The boundary condition in the case of live variable analysis problem is, in the exit basic block, no variable is live. So that is the boundary condition. And in the available expressions analysis problem, we know in the entry basic block, no expression is available. So it's an empty set. That is the boundary condition there. In the case of live variable analysis problem, the meet operator is union, and we call this as may analysis. Whereas in the available expressions analysis problem, the meet operator is intersection, and we call this as must analysis. If you look at this is we know in the live variable analysis problem, out of B is equal to union of the successors of insets of the successor basic blocks. So this is wrong. This should be out of B. Anyway, so these equations we have seen in detail. And the last part is very important. So here we are starting with an under approximation. And here we are starting with a over approximation. So this is all we have about the data flow analysis. And so if you are able to compare and contrast this live variable and available expressions analysis in detail, then you are in a very good shape. And as a part of one of the homeworks, I will give you a couple of data flow analysis problems, which you can work out by yourselves and get a good understanding. That's all I have for today. So thank you. And if you have any questions, you can ask me now.